Casca Designs is a Vancouver-based premium footwear company. On their quest to create the ideal everyday shoe, Casca prioritizes quality and comfort above all else. This commitment to comfort is demonstrated in SmartFit, a custom 3D printed insole tailored to each wearer's unique foot profile. With no two insoles being exactly alike, quality control can be challenging. Our project is an autonomous quality control rig capable of measuring physical properties of the SmartFit insoles to confirm that they have printed correctly and will perform as expected. This device serves to satisfy two use cases, one in which the insole must be confirmed to have the correct amount of cushioning, and the other in which the insole has been mixed up and needs to be identified. The means of accomplishing the latter include confirmation of the length, chirality, and arch height, whereas the former can be achieved by measuring compressibility and weight. The length and chirality validation serve to determine whether a specific insole is matched to the correct QR code, as the combination of both is highly unique across clients. The target chirality, left or right, is directly retrieved from the database, while the target length is calculated based on the insole STL file using the NumPy STL package. To calculate the measured length and chirality, a frame from the camera is first masked using OpenCV color detection. The X and Y coordinates of the top point on the mask can then be found as shown in the top right diagram. The chirality is dependent on which side of the center line this top point is. The length is calculated by multiplying the Y coordinate with the conversion factor and adding an offset. The weight validation was originally intended to be a high-level filter to determine whether or not an insole was under-extruded. This validation compares the calculated theoretical weight to the measured weight from the rig. The weight module on the QC rig is comprised of 4 strain gauges in a Wheatstone bridge configuration that converts electrical resistance into physical load. The compression validation compares measured compression stress to an experimentally determined baseline. The basic premise of the compression test is straightforward. A linear actuator extends and compresses the heel by 6 mm, and the strain gauges used in the weight module return the stresses. Comparison of the printed and expected arch profiles is an additional means of verification that the correct insole was printed. A row of fixed time-of-flight sensors were used to obtain measurements of arch height at specified points. A stepper motor and timing belt move the bed along guide rails so multiple measurements along the length of the insole can be collected to create the arch profile. The measured heights are then compared to the same points in the STL file. One of the requirements outlined by the Casca team is the ability to communicate with their data storage solutions. In order to do so, Casca exposed several REST APIs to retrieve and update the chirality, expected weight, and arch measurements of an insole, as well as retrieve the STL file from which the insole was printed. The rig is controlled by a Raspberry Pi computer and an Arduino board. The Pi manages the user interface, calculations, process logic, as well as the communication via APIs, whereas the Arduino takes care of the metric validations. The test suite consisted of 27 insoles across a range of sizes and chiralities. In this testing, the device successfully identified under-extruded and mismatched QR insole pairs 100% of the time. To evaluate consistency, the same insole was tested 5 times. The device assigned the correct designation 100% of the time, with a 0.18% variation in measured length and a 1.16% variation in compression, which are considered to be negligible. Lastly, a set of 5 trials was conducted by a different technician, resulting in a 100% success rate, indicating that the device is easy to use and reliable across different users. This quality control rig managed to fulfill its intended purpose in correctly identifying under-extruded and mismatched insoles. Although it fulfills the outline requirements, recommendations for future work include optimization for weight and arch measurements.